Alright, what's up guys? In this video we're going to pick up some vector calculus. We're going to be talking about flux and vector fields again. So we're just asked to find the flux of the vector field F is equal to x comma y comma z. That's going to be our vector field F there. And it's going to be through the half sphere. Z is equal to the square root of 1 minus x squared minus y squared. So the first thing that we need is to get the equation of the sphere. Let me remind you of what that is. So let's get the equation of the sphere. So remember, the equation of the sphere, that's going to be x squared plus y squared plus z squared is equal to a squared. Okay. In our particular circumstance, we're given z is equal to the square root of 1 minus x squared minus y squared. So what I'm going to do is square both sides of this equation here. And if I do that, I'll get z squared is equal to, well, if I square this square root, I just get what's under it, which is 1 minus x squared minus y squared. The next thing I'm going to do is I'm going to add x squared plus y squared to both sides. And if I do that, then I'll get x squared plus y squared plus z squared is equal to 1, which means that my sphere here will have a radius of 1, okay? And basically what we want is the flux. So what we're going to use is Gauss's divergence theorem, or just divergence theorem. Maybe you didn't hear it called Gauss's divergence theorem. Remember what Gauss's divergence theorem allows us to do. First of all, it allows us to get the flux, but also it allows us to relate, just a generalization, allows us to relate surface integrals to triple integrals. So remember that the divergence theorem, we have our surface integral f dot n ds. And remember, that's equal to the triple integral, also known as a volume integral, depending on the context. And we're going to have our three-dimensional divergence. And that's going to be Gauss's divergence theorem. And so basically, the surface integral over here will give us basically our flux of the vector field. I'll just say flux of F. And over here for our triple integral, again, this will give us our divergence, our three-dimensional divergence of our vector field. Okay. So this is probably one of the most important theorems in all of vector calculus, and this is used a lot along with Stokes' theorem in electrodynamics and a variety of other courses as well. So let's get the three-dimensional divergence out of the way. So remember that the three-dimensional divergence is just the dot product of the del operator and our vector field. And so it's typically denoted div f. Again, it's just the dot product. And it's just the partial of f with respect to x plus the partial of g with respect to y plus the partial of h with respect to z. So if we go to our vector field, we need to get the divergence, so let's get that out of the way. That'll take care of half the problem here. So we just need to take our partial derivatives. So that's going to be the partial respect to x, the partial respect to y, for y, and the partial with respect to z for z. So clearly here, I'm going to go to another sheet because we're going to run out of room. Let's put it right there. So clearly, for our divergence here of this vector field, we're just going to end up getting 1 plus 1 plus 1 which is 3. So the divergence of the vector field is 3. So that's what our divergence is going to be in this case. So that's the first thing that we needed to take care of. Alright. So essentially now we'll have our triple integral. And again, our divergence was 3. Now keep in mind, this was, they want the, basically we need the formula for the volume of a half sphere. And remember that the formula for the volume of a half sphere will be 2 over 3 pi r cubed. So that's what the volume of a half sphere. So remember that the formula will be different if we're talking about the full sphere. We're talking about the half sphere, so we have to modify the formula. So again, remember when we basically got the equation that we were given at the beginning, z is equal to the square root of 1 minus x squared minus y squared. When we basically got that in the correct form for the equation of the sphere, we got a radius of 1. So, and we also now know that the volume for the half sphere again is 2 over 3 pi r cubed. So basically what that means is we'll essentially have, to get our flux, we would essentially just end up having 3 times 2 pi, or 2 over 3 pi, because recall that 1 cubed is 1, so that would take care of the r cubed. And if we simplify this, the 2 3's will cancel out, leaving us with just 2 pi. And that's going to be our flux. So your final answer here for this problem, we can say that the flux of our vector field, and all we did was use Gauss's divergence theorem. So the flux here, we'll say the flux of F is 2 pi. And that is your answer. Okay, so let me get my marker here and I'll circle the answer for you. And this was a pretty straightforward example. And I have plenty of examples, other examples on video as well of us using Gauss's divergence theorem, Stokes' theorem, Green's theorem. Feel free to check out my videos on that should you need it. But that's going to be it. And let me know if you got any questions. And I'll see you guys next time.